In this video, we continue with Chapter 5, studying Section 5.5, Applications of Inner Product Spaces. Our learning objectives for this video and the next are to find the nth order Fourier approximation of a function, to find, given a subspace with an orthogonal or orthonormal basis, to find the projection of a vector onto that subspace, and to find the cross product of two vectors in R3. So we will look at cross product in the second video. So recall from theorem 5.15 that the projection of V onto S is the unique vector in S that is closest to V. So theorems 5.14 and 5.19 combined tell us about projection onto a subspace and the least squares approximation. So if U1 through UN is an orthonormal basis for a subspace of a vector space V, so remember, since this is an orthonormal basis, each vector is orthogonal to every other vector in the basis, and also these are unit vectors, so that's why we're using U1 through UN here to denote these vectors. And if V is a vector in V, then the projection of V onto S is calculated by the inner product of V with U1 multiplied by the vector U1, and so on through the inner product of V with UN multiplied by the vector UN. And remember, these inner products are going to give us scalars, so the coefficients for this linear combination. If vector space V is a space of functions, for example, V is the continuous functions on the interval AB, so that the UI are functions, then we can say the projection of the function f onto S is a function inner product with U1 multiplied by U1 plus the function inner product with U2 multiplied by U2 all the way through the function inner product with UN multiplied by the function UN. And so this is the least squares approximating function f with respect to S. So here is the outline of the proof. We will show that the projection of V onto S from this formula by showing that V can be written uniquely as the sum of a vector from S and a vector from the orthogonal complement to S, or S perp for short. V can be broken up then into S1 plus S2, where S1 belongs to vector space or subspace S, and S2 belongs to the orthogonal complement of the subspace S perp. So then by definition, the projection of V onto S equals S1. And so over here, we've got a diagram showing that V can be a combination of S1 and S2. So we're going to let S1 be V inner product U1 multiplied by U1, V inner product U2 multiplied by U2 through V inner product UN multiplied by UN. And we're going to let S2 be V minus V inner product U1 multiplied by U1 minus V inner product U2 multiplied by U2 all the way through V inner product UN multiplied by UN. Then S1 in S, then S1 is an S because it's a linear combination of vectors in S. And for each basis vector UI of S, UI inner product with S2 is going to be broken down this way, where S2 is in the orthogonal complement of S. So we're going to have UI inner product with just substituting in S2, this V minus V inner product with U1 multiplied by U1, subtracting all the way through V inner product with UN multiplied by UN. And so then that is going to be simplified to be UI inner product with V minus V inner product U1 multiplied by UI inner product U1. So here we're using the properties of the inner product space and so on. And then we're going to get zeros here everywhere except UI inner product with V. And then when we have V inner product with UI multiplied by UI inner product with UI, that UI inner product with UI is going to be a 1. And remember, we're getting zeros everywhere else because these are orthogonal. So because they form this orthonormal basis, the inner products of all vectors that are not the same vectors in U are going to give us 0 there. Okay, so since all vectors in S are linear combinations of the U's, this set of the UIs, S2 is orthogonal to all the vectors in S, so we can say S2 belongs to the orthogonal complement of S or S perp. All right, so we know from section 5.3 that this set 1 cosine x, sine x, all the way through cosine nx, sine nx is an orthogonal set using this inner product, the integral from 0 to 2 pi of f of x multiplied by g of x, all integrated with respect to x. And so let's go ahead and normalize that set. Remember, we are on the set of continuous functions here from 0 to 2 pi. All right, so the norm of 1 squared here is going to be the integral from 0 to 2 pi of 1 multiplied by itself with respect to x integrated. So that just gives us a 2 pi. For n's that are non-zero, the norm of cosine nx squared, following our formula for this integral, is going to be x over 2 minus sine nx multiplied by cosine nx over 2n. And that gets evaluated from 0 to 2 pi. And so that works out to be pi. And then the norm of sine of nx squared is going to be the integral from 0 to 2 pi of sine nx multiplied by sine nx, all integrated with respect to x. And so that's going to be x over 2 plus sine nx multiplied by cosine nx over 2n. And when we evaluate that from 0 to 2 pi, that's also pi. So our orthonormal set here is 1 over root 2 pi, 1 over root pi cosine x, 1 over root pi sine x, 1 over root pi cosine x, cosine 2x, and so on till we end with 1 over root pi cosine nx and 1 over root pi sine x. So these all are orthogonal vectors to one another, and then they have length 1 now, so they're unit vectors. So we've normalized the set, and we're here on the set of continuous functions from 0 to 2 pi. So the nth order Fourier approximation of a function f on the interval 0 to 2 pi is a projection of f onto this span of this orthonormal basis we've set up. So Fourier approximations are useful in modeling periodic functions, such as sound waves, heart rhythms, and electrical signals. So here's some examples of common Fourier approximations we see. So we see we can use a Fourier approximation for a square wave in this first diagram. And then you see different orders of the Fourier approximation. So you can see as the waves get closer to the square, we're at a higher order. So like the orange curve there would be probably the third order maybe, and then, or the first order maybe, and then and so on, it gets more and more precise. And then the second graph shows what's known as the Sawtooth Wave. So you see we can approximate the line there with a Sawtooth Wave. We've got a triangle wave down here in the bottom left. So we see as we get higher order, you know, closer to the, let's see, the blues and the greens and the yellows, we're getting closer and closer fit to that triangle wave. And then the semicircle in the bottom right. And so we've got, as we see higher orders closer to the blues and the greens there, we're getting a better fit to the semicircle with our Fourier approximation. So in this example, we're going to find a second order Fourier approximation for this periodic function f of x equals pi minus x for x in 0 to 2 pi. We're leaving the 2 open, so we're not including 2 pi, but 0 is closed. And f of x plus 2 pi is going to equal f of x. So our solution here, we're going to set g of x equal to the inner product of f and 1 over root 2 pi multiplied by 1 over root 2 pi, plus then we've got f inner product with 1 over root pi cosine x and all that gets multiplied by 1 over root pi cos x. And so remember, these values here are coming from our orthonormal basis. So these are the orthonormal basis we found by normalizing the orthogonal basis that we found in an earlier video. And so on until we end up here with our last term is going to be the inner product of f with 1 over root pi sine of 2x. And that value is going to get multiplied by 1 over root pi sine of 2x. All right, so we're going to use software to evaluate the integrals. So I've put the values in here. You can double check using Wolfram Alpha or GeoGebra, I believe, or potentially your graphing calculator could do this, although it might be a little bit messy for a TI. And so we get 0, 0, 2, 0, and 1. And so here is our second order G2 of x equals to 2 sine 2x, and that 2 is coming from right here. And then plus 1 sine of 2x, so that coefficient 1 is coming from here. And so we see it's a so-so fit. That's our pinkish curve fitted to the line there. And so the first graph was our function pi minus x. All right, it's common notation with the Fourier series to write the coefficients as a naught equals 1 over pi, the integral from 0 to 2 pi of f of x dx, and then a sub k here is 1 over pi, the integral from 0 to 2 pi f of x cosine kx dx, and then b sub k is 1 over pi, integral 0 to 2 pi f of x sine of kx dx. You probably saw these coefficients in calculus class. If not, this is a Fourier series, and you can do more reading on Wikipedia. You've seen already how we can use it to model functions with periodic functions. So the nth order Fourier approximation here, we call it G sub n of x, is going to be a naught over 2 plus a1 cos x plus b1 sine x, and so on until you end up over here with an cos nx plus bn sine nx. And so you can see as the orders increase, that's why our graphs back here were getting more and more accurate, because you've got a linear combination of more and more periodic functions, making your Fourier series fit the triangle wave or the semicircle or the sawtooth or the square wave much better. Okay, so now we're going to take a look at an example where we are given a subspace with an orthogonal or orthonormal basis, how to find the projection of a vector onto that subspace. All right, so we are given that S equals, these two vectors are an orthonormal set, and R3 and our two vectors are negative root 2 over 6, root 2 over 6, and 2 root 2 over 3. And our second vector is 2/3, negative 2/3, and 1/3. And then we are going to find the projection of V, where V is what we think of as the I vector, or 1, 0, 0, or the first of the standard basis vectors in R3, onto the span of these two vectors. So here's our solution. So the projection of V onto S is going to be the dot product, because we're in R3, that's our inner product space, of 1, 0, 0 dotted with the first vector, all multiplied by the first vector, plus 1, 0, 0 dotted with the second vector, all multiplied by the second vector. And so that works out to negative root 2 over 6 from the dot product of the first dot product, multiplied through by the first vector, plus 2/3 from the dot product of 1, 0, 0 with the second vector. So notice in all of these, we're just pulling out the first elements because we're dotting with 1, 0, 0. And so when we combine everything, we end up here with 1/2, negative 1/2, and 0. Okay, in the next video, we are going to look at the cross product.